In this video, we will talk about what local and absolute maxima and minima are. So I want to begin by defining these terms, and then we'll look at an example with a graph to get a better visual sense of what they mean. All right, so here's the definition. Let the domain of our function f be D. So I'm calling the domain D. And C is a number in the domain. Then f of c is the, and now there's a few different parts to this, and I'll start to fill these in. But before I do that, when it says that c is a number that's in the domain, that means that c is an input. So a number that's in the domain is an x value. It's something that I plug into my function. And on the flip side, f of c is my output, or it's my y value. So we say that f of c, the output, is the absolute maximum value of our function f on our domain D if, and there's some condition here that I'm going to fill in, but intuitively what the absolute maximum value should be is, I want it to be the highest point on the graph on whatever domain we're talking about here. So okay, so here's the condition that I need to specify that this output happens to be the highest one. I would say that f of c, this output, is greater than or equal to f of x. That's saying it's greater than or equal to every other output. And it's specifying that when it says that this is true for all values of x that are in the domain. Okay, so this is the technical way to define an absolute maximum value. All right, so next let's define an absolute min value. So we say that our output f of c is the absolute minimum value of our function on the domain D. Intuitively, we want this to be the lowest point on the graph. And the condition we need for this is, we would need that f of c has to be less than or equal to f of x for all x in the domain. So this is saying that the output, when you plug c in, that value, f of c, needs to be less than or equal to any possible output that we could have. All right, so those are the definitions of absolute max and absolute min. All right, so one quick thing I want to note before I get into the definitions of local max and local min is, so I want to note that max and min values are collectively called, extreme values. So if we have a question that asked us to find the extreme, maybe the absolute extreme values for a function, it wants us to find the absolute max values and the absolute min ones. So extreme values means both, maxes and mins. All right, so now let's get to the third definition here. So the third definition, now we're going to define the local maximum value. So our output f of c is the local maximum value of f of our function on the domain D if, really similar condition at the start, f of c is greater than or equal to f of x. But this time, I say that this is true on some open interval containing c. Okay, so conceptually what this will be is, typically in a graph, this looks like a peak. So intuitively what this definition says is the output f of c needs to be greater than or equal to the outputs that are near it. That's what the on some open interval containing c sort of refers to, just in loose language. All right, so finally we can define local minimum value in a very similar way. The thing that I would change about this is I would say that f of c needs to be less than or equal to f of x on some open interval containing c. And conceptually, this would look like a valley, typically in a graph. So a low point in a graph. So sometimes local maxes and local mins, we call them relative maxes or relative mins. So these are also called relative max min values. Okay. Absolute max min values are sometimes also called global max or min values. All right, so let's look at an example. So here is our first example. We have this graph, and let's label all local and absolute extrema on this. So extrema means all extreme points. So that means maxes and mins. All right, so let's start off with the absolute max. Remember, the absolute max, looking back up to our definitions, is the highest point, the output that has the highest y value. Okay, and there are 2 points that have the same sort of largest y value here. And they happen to be here at -3, 5, and here at 1, 5. So the absolute max actually occurs at 2 points here. The absolute min, the lowest point on this graph, would be here at 5, -2. That's the absolute min. The lowest y value occurs at that 1 point. So next, let's label the local max. Okay, so for local max and local min, pause the video for about 1 minute and see if you can label where those would be using our definition of local max and local min. Remember, these don't have to be the very highest point on the graph or the very lowest point on the graph. They just have to be higher for local max than the points sort of immediately around it on some open interval, and similarly for local min. So pause it, 4, 3, 2, 1, pause the video. Pause it for a minute to try to label the local max and local mins. All right, so hopefully you've done that. Hopefully you've tried that for about a minute, and hopefully you have an idea of where those might be. Okay, so for local max, there are 2 places. There's sort of 2 peaks here, and there's one at 1, 5, and there's one here at -3, 5. Okay, so that could happen. Sometimes the absolute max and the local max happen to be at the same place. For local min, so local min, it turns out there is a local min at -2, 3. Even though that's not the absolute min, that's totally fine for being a local min. There is an open interval around -2. In fact, if I were to go sort of this far in the direction to the left and this far in the direction to the right, and if I were to look at my graph on that interval, the point where -2, 3 occurs, that's the lowest point within that interval. Okay, and that's what makes this a local min. Okay, there's another place where we have a local min though. The other place that we have a local min is 2, 1. And that one might look weird because this one doesn't look like a valley. But this description, like these descriptions like peak and valley, they're just general descriptions. It doesn't mean that they apply to every single scenario of what a local max or local min would look like. To really be thorough, we have to make sure it satisfies the definition. And in the case of this point 2, 1, if I were to look at some open interval around where this is where 2 is, and if I were to look at the part of the graph within that interval, so to look at the outputs within that range, so if I were to look at that part of the graph, and then look at where the actual point is right there, the point at 2, 1 is definitely the smallest within that open interval. So that, by definition, is a local min. All right. And there actually is no local min where the absolute min is. So the absolute min is not also a local min in this problem. It's something to do with the fact that this point occurs at an endpoint of my interval here. So I'll write that down a little bit more explicitly in just a minute. But I just want to show you what it would look like if I wanted to write down one of these things in words. So if I wanted to write down something like my absolute max, this is how I could write it down. I could write down my absolute max value. So by value, it means what is the actual output? What is the y value? So when you see that specific word, value, if it's talking about absolute max value or absolute min value or even local max value or local min value, it means the y value. So the y value where the absolute max happens is 5. And then sometimes the question will also ask, well, where does that max or min occur? And so this one occurs, when it asks where it occurs, it means what's the x value where it happens? Well, this occurs when x equals a -3 and also when x equals 1. So it occurred twice. All right. If we wanted to at this point, we could also write down similar things for the absolute min value and where it occurs, and the local maxes and local mins, and what those values are and where they occur. But it's really similar, so I'm going to just leave it at this one. Our example technically just asked us to label all the local and absolute extrema, and we have labeled all of them in this picture, so that part is already done. All right, so I mentioned I would note something about the endpoint. So an endpoint cannot be a local max or min, since any open interval containing it would extend outside the domain. So if we look back to our picture, if we looked at this right endpoint here, where our domain sort of ends when x equals 5, if I try to take some open interval around this, so an open interval around it, so I'm drawing parentheses there to indicate that it's an open interval. That means I can go all the way up until this this point right here, but I'm not allowed to be equal to wherever that parentheses is. And same thing with the parentheses on the other side. So if I were to draw an open interval like this around where x equals 5, the stuff to the right of 5 within this interval is not actually a point, doesn't correspond to a point on the graph. It's outside of my domain. And that's a problem here. That's why we're not going to count endpoints as local mins or local maxes. That's the convention that our book uses, and I'm going to be following that. There are other textbooks that adopt different conventions, but I'm going to be sticking to the convention that our book follows. All right, so let's do another example. So I have a couple graphs here, and let's state the absolute max and min values if they exist. Okay, so in part A, we have this sort of parabola graph, upward facing parabola, and the vertex is at 0, 1. So in this graph, the absolute min value, the smallest y value we have, is clearly 1. It's where the vertex happens. For absolute max value, that's asking what the largest y value is on the graph. And when there's no domain specified in these pictures, that means we want the domain to sort of be like the largest possible natural thing. In this picture, it means the domain is everything. It's all reals. So what's the largest y value at any point on this graph? And the answer is there is none. There is no single largest y value. None, since there is no largest y value. They get infinitely larger So that's why there's no absolute max value. Okay, so what about in graph B here? So graph B, this should be connecting with that point where this closed circle is. All right, so we have this sort of segment of a graph. There's a dot here, closed circle at 4, -1, and an open circle at 1, -3. So in this picture, I see the absolute max value, the largest y value is in -1. Absolute min value, the smallest y value, is none. So why is that? Why is there none? It's since it might seem like the min value is -3, but if we think about it very closely, since what happens is the y values can get close to -3, but never reach it because of the hole, but never reach it. So it would be incorrect to say that -3 is the absolute min value, because that would imply that I do reach a y value of -3 somewhere, but I never actually reach it in this graph. I just get really, really close to it because of the hole, but never actually reach it. All right, so what I want to end this video with is by stating a theorem that'll state a condition that'll guarantee for a special type of graph that will always have an absolute max and an absolute min somewhere within our domain. So it turns out that if my function f is continuous on a closed interval, so notice we have these closed brackets at a and b. So if my function is continuous on a closed interval, then my function will definitely attain means it will have, for sure, an absolute max and an absolute min. So in part A, my function was continuous, but its domain, the domain we were looking at, was all real numbers. It wasn't a closed interval. In part B, we weren't looking at a closed interval. It's what's called a half-open interval. In part B, our function is continuous on a half-open interval. Okay, and because of that, it doesn't quite fit what this theorem says. In the next video, we'll go over a method for when we have a function that is continuous on a closed interval. How do we find the absolute max and the absolute min values? All right, so in terms of our goals, we've defined all of those terms: local mins and maxes, absolute mins and maxes, and we've talked about what they look like graphically. In the next video, like I just mentioned, we'll talk about how to find an absolute max and an absolute min algebraically with some calculus.